Hello everyone and welcome back. Today we're going to be talking about Bayesian inference as a worldview. So I'm not going to be asking you to do a lot of intricate calculations with Bayesian updates, but I do want you to understand how they work and what they can tell us about a way of becoming more right or being less wrong over the course of time. So what is Bayesian inference? It's a way of updating your views and opinions and beliefs based on incoming information and also based on what you already believe. The idea is basically this. You have some particular issue, and then there are different things that you might think about it. There are mutually exclusive things that you might think about it, ranging from things that you maybe consider highly plausible to some things that you think are almost certainly not true. And then each of those can be assigned a certain percentage, representing how likely it is to be true, or how strongly you believe that particular thing. And this gives you a distribution of possible beliefs with probabilities associated to each. So here, just as an example, I've drawn up a distribution of 5 different theories, right? So we have each color represents a different theory, and then a certain amount of belief associated to each one. So 40% for theory 3, theory 1 gets 20%, theory 2 is 15%, and so on, right? You can read that off of the axis over here. And all together, these add up to 100%, right? Because something has to happen, right? And so what happens then is you start with this distribution of beliefs and you start making observations or running experiments. Every experiment that tests a given theory or experience that you have that touches on your beliefs on a particular topic is a new piece of information. And each new piece of information should alter your distribution of beliefs, usually only by a tiny bit. But if something's really unexpected from your current worldview, then it might change it quite a lot. It might really change your point of view. If an experimental result or observation teaches or matches a theory well, then that means you should maybe believe that theory a little bit more. But if the experience does not match the theory well, then your belief in that should go down. So what we'll see is here's our same distribution to start thing, that's my initial, and then maybe after the first experience or experiment, things change a little bit. So you see that the gray goes down, the yellow goes up, the light blue remains about the same, so does the orange, and the dark blue goes down a little bit. So whatever it was that happened in this first experience, it didn't match so well with the gray theory, but it matched pretty well with the yellow. And the others are, more or less affected by it. It's more or less likely in each of those cases. And so what you see is as each experience happens, you get a change in the distribution. And the larger one of these bars gets, the more you believe that thing, the more that seems to be your right explanation of what's happening. So you can trace what happens with these various beliefs as we go through. So for example, the gray, it goes down, stays about the same, then goes up and goes down again. So in the end, it's gotten about half as powerful as it was before. The dark blue just consistently goes down. Whatever theory that was, it's not doing a very good job of matching with the world. Light blue goes even, down, up a little bit, and then back down to much lower than where it started. And you see the yellow is going up significantly, gets a little bit of a setback, doesn't maybe match quite as perfectly in experience 3, and then after 4, though, it's way up at 65%. So over time, you should see this distribution converging to having lots of probability in the thing that's most likely to be true, and very little probability in the things that are probably false. So this is a way of moving toward a correct answer, a hopefully correct answer, while never losing sight of the fact that you're never going to be 100% certain. In fact, if you are ever 100% certain about something, in this Bayesian framework, it encapsulates exactly what you would think that would do. What would happen? If you're 100% certain about something, you see some evidence, it matches, doesn't match, doesn't matter. You're still certain. You're stuck in that way of thinking. But as long as you have some uncertainty involved in different possibilities in your mind, even if you're giving them only the very slightest percentage chance of being correct, then when new evidence comes along, you can make an adjustment. And that's one of the things to take away from this frame of view. All right, so I have actually run an experiment. I as when I was talking about p-values, I ran an experiment with a coin, and I took a fair coin and flipped it 100 times. Now, let's suppose that at the beginning I didn't know it was a fair coin. I just had a coin that I was starting to flip, and I had all of these different possibilities in my mind about how this coin could be behaving. It could be have a 100% probability of coming up heads all the way as this extreme, or a 0% probability of coming up heads, and everything else in between. 90% heads, 40% heads, so 60% chance of coming up tails. The fair coin is there in the middle, 50-50. And I'm going to start out pretty agnostic about these things. All of these I'm assigning a 10% probability in the middle. So 10%, 10%. All of these I'm giving the same weight. I think they're all equally likely. The ones on the very extremes I'm going to do a little bit lower. Right, so 0.05, only a 5% chance that it's always going to come up heads or always going to come up tails. So then what I did is I flipped this coin 100 times, and after each one of these flips, I adjusted the probabilities. And I'll show you some of the results of how these Bayesian updates changed the distribution of beliefs. So here's the initial setup. So you see the two extremes get 5%, everything else in the middle is 10%. So everything's flat, right? We get that nice flat curve. Now, after 10 coin flips, it's not flat anymore. The ones on the very end are actually gone completely because something impossible happened. Basically, if it were true that this coin is always going to get heads, and then I see a tail, now I know for certain that that theory is definitely wrong. So it's gone. It becomes 0% and it stays that way forever. Similarly, this one on the end, on the right-hand side, says that that this coin would always come up tails. So as soon as I see a head, I know that that one's definitely wrong. It goes down to 0. None of the other things can definitively be ruled out, but the probabilities on the extremes get very, very tiny over time, and you can barely see them going forward. So in any case, we can see here what the distribution is after 10, 20, 30, 40, and 50 experiments. Right? And we see things kind of accumulating toward the middle, which makes sense because it is actually a fair coin. So the system seems to be working a little bit. So after 10 experiments, we can see that the most likely thing is that it's a 60% head coin. That's around 28%. Looks like around 22% chance that it's a fair coin. About a 12% chance that it's biased 60% towards tails. And about we have yellow here. With 70% chance of heads, there's about 22% chance of that. So you can see it kind of concentrating and concentrating. And so, but looking at the individual things, you see blue, the light blue, gets very large over time, just keeps going up. Yellow moves up, but then experiences a bit of a regression. Green, which is that the coin is fair, so this is actually the true theory, though we don't know that from experiment, right? I know that because I set it up that way. But green initially grows, goes down, and then it kind of fluctuates a little bit. So it's a bit strange to see that the true answer is not approached automatically the first time. So after 50 experiments, this model, this Bayesian update is saying that the 60% heads, so the idea that the coin is 60% biased towards heads, has over 50% of the probability. It's way up here at like 56%. Now that turns out to be because when I tossed these coins at random, in the first 50 tosses, there were 31 heads. So 62% of the heads were, the coin tosses were heads. So its system's doing a pretty good job. If you tossed a coin and you got 60% of the time you got heads, you would think that that is a coin that is biased to 60% heads. Makes total sense. Well, let's see what happens. I continued doing this experiment. I went to 100. And we see something quite different happen. So we see that over the next 50 experiments, here's where we were before, the blue, which is the 60% biased coin, goes down, 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 and down. And all of this probability concentrates in green, the fair coin conjecture. And in the end, after 100 experiments, we have almost 80% likelihood that it's a fair coin, less than 10% probability that it's biased towards heads, and about 15% probability that it's slightly biased toward tails. And that turns out to be because in the second 50 tosses, there were 18 heads. So in the end, I ended up with 49. And this method can see those trends, right? It's a mathematical thing. It doesn't think, it just grinds out some numbers. But in the end, if you keep taking the observations, even if at halftime here we weren't getting the right conclusion, we knew that the right conclusion, we had it in our realm of possibility here, but we weren't giving it a lot of weight. But continued experiments, continued experience led us eventually to most highly believe the thing that we think is probably true. So this is the way Bayesian updates or Bayesian inference works, by continually taking on information and improving, hopefully improving, getting us closer and closer over the long run to the truth, right? And basically it's the law of large numbers at work to our advantage. We're using the fact that over the long run, our observations should match with the correct theory, right? So giving all the theories a chance, and then we'll eventually converge to the right thing. So what can you take away from this? Well, I'm not expecting you to do a bunch of calculations as you're walking around every day on the street. That's just not the way people work, right? To actually get the numbers like I did in a very controlled experiment is tricky. There's some tricky calculations that you have to do. Nonetheless, this is a useful mental framework. It's a way of seeing things, if nothing else. It's a way of viewing how science works in some ways. And I think it helps to clarify some of the issues that arise when exploring new things. So this is useful mental framework. Basically, the idea is take every experience as an opportunity to challenge and refine your set of beliefs and the strengths with which you hold those beliefs. Right, so you just take on the information and allow yourself to be influenced by the things that you see, right? And give yourself opportunity to have those observations, to challenge your points of view, and that will get you moving toward more belief in the things that happen to be true. So takeaways: always be open to new evidence and experiences that might change your point of view or belief. And in particular, don't always look for evidence that confirms what you already think. Because it turns out that if you look for evidence that confirms what you already think, then the Bayesian distribution won't change, or it will barely change. It's only by giving a chance for unusual or unexpected things to happen that you can ever change a viewpoint in this framework. Thought of the other way, the only way you can really get stuck in an incorrect idea is by not challenging it, by not giving yourself a chance to start to believe differently than you currently do. Similarly, never rule anything all the way out unless it's been proven definitively false, which is exceedingly rare in the real world. It's only truly dogmatic or simplistic views can be eliminated in this way, because everything else, even if it's very unlikely, is still possible given the world that you've observed. And then finally, over time, you expect your understanding of the world will converge more and more toward a good approximation of the truth, which hopefully is what we're all looking for. And even though you should always be open to change, no matter how close you get to the truth, you should always be open to the idea that maybe you're missing something. So this is also, like I said, it's also useful for thinking about science, right? Science is about constantly refining our understanding of the world around us. Sometimes that means taking an old idea and totally throwing it out. But more often it means taking an old idea and adding nuance, adding complication, looking around the edges to see where things might fall apart. But we're always challenging our understanding. And that's why we talk about things like the theory of gravity. Now that theory, if I showed you that graph, would have a very high spike for gravity and a very low spike for gravity not really being a thing, right? We've moved toward that, but we're always open. We're always open to the possibility that things aren't the way that we've understood them before. And so hopefully this helps to clarify a little bit of what's going on with Bayesian updates. Have another read through the chapter and look at some of the examples they talk about there. It's really a very useful way of thinking about the world.